lung X-ray images preprocessing algorithms for COVID-19 diagnosing intelligent system. Effective treatment of COVID-19, first of all, requires the development and implementation of prompt and accurate diagnostic tools for this disease. In this regard, currently the most common method of rapid diagnosis of COVID-19 on a global scale is based on the examination of X-rays of the lungs. This technique has many well-known advantages, but there are also important disadvantages. Mainly, this is poor visibility and low contrast of not expressed foci of the disease. This is especially true in the early stage of COVID-19. The analysis of such images is difficult. Therefore, when analyzing X-ray images of the lungs, the time of data analysis can significantly increase, as well as inadequate diagnosis. The aim of the research is to develop mathematical models and methods for preprocessing lung X-ray images to ensure subsequent effective diagnosis of COVID-19 in terms of time and accuracy. The objectives of the research are to develop methods for efficient cleaning and improving X-ray images. X-ray images of an open dataset are considered as initial data for analysis and experiments. All files are in DCOM format. They are already annotated. Several examples of such images are shown below. Dataset images can differ significantly from each other. The main differences of the images are given below. To understand the essence of the proposed preprocessing algorithms, in addition to the images, we also consider the density histograms. Artificial objects in the image give peak density brightness, distorting the histogram. Therefore, the basic set of preprocessing algorithms will be aimed at solving the problems of eliminating artificial objects and their influence on the image histogram. A combination of three preprocessing methods is proposed. Histogram shift compensation. This step is required for standardization and resistance to negative values. We will eliminate the shift in the density range to the non-negative part in the presence of negative values. Image inversion and bias compensation. This is the second method. And the third method, image density scale normalization. This step is required for standardization the image and scale formats. The first two methods are standard. The third method has been developed as a brand new. The main steps of this method are presented below. Based on the proposed methods, has been developed software that allows preprocessing of X-ray images of the dataset, as well as visualization of the original images and the results of their preprocessing. To confirm the effectiveness of the proposed methods for images preprocessing, a series of experiments was carried out according to the following scenario. First experiment. X-ray images of the lungs are not preprocessed, but are immediately fed to the input of CNN efficient net for classification. After that, a matrix average precision is calculated. The second experiment. X-ray images of the lungs are preprocessed according to the proposed algorithms. After this, the images are fed to the input of the CNN efficient net for classification. After that, a matrix average precision is calculated. After that, a comparative analysis of the results of two experiments is carried out. The typical application results of applying the proposed methods are shown below, pairwise histograms of the original and preprocessing images. After preprocessing, we were able to localize the informative range of the lungs region of interest with high accuracy and improve the images, make them more saturated and contrast. The application of standard CNN models for classification to such images showed an increase in accuracy by more than 1.5 times. As a result of preprocessing, not only the probability of adequate lung extraction increases, but also the accuracy of predicting the presence of the disease and the stage of its development increases by 2 or 3 times. Perspective models to improve of X-ray images preprocessing algorithms are shown below. There are two models. Conclusions are on the slide 15 and slide 16. Thank you for attention.